talk up here.
You can use this, or you can use the projector if you want.
Right.
We can come up.
And I need to turn this on. Right. Reg laptop. Projector, is it starting up? I don't know if I want to press the projector off button. What's this? Is that starting up? Yes, it is. Right. Okay, so if I get this over on me here, right. Okay, so what we're doing is we're talking about optimization, right? Because you guys asked me about.
You clap.
Just seeing if the lights work. So you guys asked me about optimization. So I thought I'd talk a little bit about the optimization lecture that I had as lecture 7 from the multi-threading course that we did last year, because we did a whole we had a whole course on multi-threaded optimization. Now most of you are using game engines, and so you don't handle the threading yourself, right? And so a lot of what we're talking about was threading in C++ and learning how to use OMP to use multiple cores. Now, in game engines, often those multiple cores are being set up for you and the threading is being done for you. However, we can still look at sort of standard optimization techniques and discuss kind of what works from a language point of view. Okay, so speeding up code, preferably by getting close to the correct first time, confirming with a runtime profiler. When you ask me about optimization, the first response that I should give and that you'll get from me is what part of your code is slow and how do you know that it's slow? Okay? Because if you are profiling your code, if you're not profiling your code, you can spend a lot of time optimizing something that isn't actually slow. Right? You can spend a lot of time creating, like saying, oh, I know this will be slow, therefore I'll put effort into it and make it fast. And the answer is, well, actually it runs during loading time. The user is already having to wait 4 seconds for the file to load. You've optimized something which is 0.1 of a second longer on that 4 seconds. So your overall performance goes from 4.1 seconds to 4.0 seconds. No user will ever notice that, right? So unless you can show me that the particular part of your code that you're worried about is actually slowing you down, unless you've got a profiler, then you're kind of just poking in the dark with your optimization. And one of the things I talk about optimization, and you know, we're game developers, and we talk about gamification. Optimization is a game for programmers, right? Because one of the challenges is that if you think about a game, right? A game has this idea of you know, you're in charge, you're making changes, and you're getting some feedback for doing things, right? And the feedback you're getting from optimization is how much faster can I make this code run? And you've got this kind of unknown space you're exploring. So you get to explore things, you're looking for an optimization. If you've got multiple people, you can compete against each other, and it becomes, it becomes very game-like, right? So optimization becomes a game that programmers play. And although it's fun to optimize, it's not necessarily effective to optimize, right? Because you can spend, you know, 2 days saving yourself 20 minutes, right? You guys are also, and computer programmers in general, are very good at thinking, oh, you know, I don't want to do this process manually. I don't want to have to copy and paste this 30 times. So what I'll do is I'll write a piece of code that does that. And then there's a bug in it, so they spend some time fixing that bug, and then they, oh, I could do it this way, and they refactor it, and they spend a day doing something that would have only taken them 10 minutes if they'd just actually copy and paste. Okay? It's a risk. When you create a script or when you create a tool for doing something, you kind of have to think, am I going to use this many times? Who am I saving time for? Right? Am I saving time for myself? Then I can do the full evaluation. If I'm saving time for my user, how many users do I expect to have? Right? Because if you can save a second for 100 million users, that's a lot of lifetimes, right? But if your system is not going to have 100 million users and you're just doing it for the 4 of you in your group to make that group faster, you might just want the manual process, because in total, the unoptimized version might be better, and you just have to wait those extra few seconds. So there are courses on optimization that some of the content has referred to. Confirming it with runtime profiling. So in Visual Studio, you get a profiler. In some of the game engines, you can spin up the profiler and get it to profile your code. And you can see whether it's your objects loadings that are the problem. Is it your mesh recalculation that's the problem? Is it something in the shader that's a problem? Is it a CPU problem? What is actually binding you up? So, profiling. Graphical profiler is much easier to work with for multi-threaded optimization. So one of the problems that you get if you use profiler, that's a text-based profiler, if you've got multiple threads, and game engines usually have multiple threads, just seeing what the main thread is doing is a problem, because the main thread will often be just waiting, right? And so you have to be able to synchronize between your main thread and your rendering thread, or your file reading thread, or your networking thread, because they're often waiting on each other. And it's the relationships between those that become interesting when you're trying to profile where your program is slow. What you're looking for in your profile space is in 2 ways. One is you're looking for sleep-wake cycles when you're doing multi-threading. And for your normal profiler, you're looking for where your code is spending all of its time. Now, have you guys used the Visual Studio Profiler at all? Not really. Okay, so for profiling of CPUs and of performance, there are 2 types of profiling. And I don't have it on there. So there are 2 types. There are 2 types of profiling, and we can scoot over to Visual Studio and I can show you those in a minute. There are 2 types of profiling. There is sampling and instrumentation. Okay, so if you're doing sampling profiling, what you're saying is, okay, you as a CPU, every 10th of a second, I'll ask you, what line of code are you executing? Right, and then it just gives you which line of code from your program is currently being executed. So you're just basically polling the CPU and asking it. And by doing that, what you do is you collect a sample of what you think is taking all the time. Right? So you go and say, like, if one function, say a file reading function or an image processing function is taking all your time, then every time you ask the CPU, what are you doing? It will say, oh, I'm processing the image. You ask it in, oh, I'm processing an image. You ask it in, oh, I'm processing an image. And you ask it to go, oh, I'm handling keyboard input. And you go, oh, now I'm doing image processing in, image processing in. So you build up a profile of when you ask the CPU, what are you doing? It says, oh, I'm doing this thing. And that highlights a line in your code. And then you can say, oh, where's the hot lines in my code? Where are the lines that spend most of their time? Whenever I ask, it's in that line of code. And the idea is that you then get a profile of sampling your CPU and saying, hey, so when you did that, what were you doing? There are two problems with that. One is that if you have a line of code that's called from multiple different paths in your file, right? That line of code has to kind of unwind itself and say, where am I called from? And so you get this overloading of code, and you're only sampling, which means you might not be seeing the full actual processes that are going on, right? Because you're just doing some sampling of the CPU. I had one problem where the Visual Studio sampler was linked to frame rate, right? So it was sampling at certain cycles per second, right? So it would be using actual time, and it would sample at it was sampling at 60 hertz, so it's sampling 60 times a second. Now I was running game code that had its frame rate synced at 60 times a second, which means every time the CPU was queried and said, "Oh, what are you doing?" it was the same pass through the frame processing. So I was actually doing, this is the AR ball game I have, and I was doing an image copy, and for some reason the red was taking 60%, it was taking 60% of the CPU was hitting the red, and the green and the blue were about 10% each, and then the rest of the code was using up the rest of the time. And it's kind of, why is 60% on that single line of code? And it's because that was the point that the CPU had got through when it's processing all the code when it was asked, because it was waiting to sync every time it was queried. It was at the same point because they were both synchronizing at 60 frames a second. So it wasn't that this particular line of code was any slower than any other line of code. It's just that every time you asked, I got to the same point in my process, and so I gave you the same line of code back, right? So you can actually set up Visual Studio now to do random sampling, right? So it doesn't sample timed at with every second. It actually randomly adjusts when it samples. So sampling is usually faster because you're not actually having to do much to code. You're just asking every now and again the CPU what it's doing. The other type is instrumentation. For you guys as game developers, instrumenting your code generally makes your game completely unplayable, right? Because what instrumentation testing does and profiling is that it puts into every function call, absolutely every function call and every system function call, every call, it puts in a timer block in the front of it and the end of it. So suddenly your code runs at about 1/10 the speed that it was running at, but you log every time a function is entered and every time the function quits, how long that was, right? And how many times each function was called. So if you have something that you really want to know exactly how often this function is called, just sampling won't tell you that, right? So sampling will just say, oh, there was a line of code here, and there was a line of code here, and a line of code there. These lines of code happen to be the ones that were in the CPU when I asked, right? But with instrumentation, you say, oh, that ran 32,000 times, right? That function ran 32,000 times because I've instrumented it. Every time where that function went in, it added it to the data file, and it also timed every time it went in, it added the timing, wrote the timing out to the data file. All of that overhead slows your code down massively and your game becomes unplayable, but you get to see everything that happens. This is quite a good way of catching if you're, say, running something multiple times when you don't intend to, right? If you're like loading I've seen this with someone was using Lua, and when they instrumented, they found they were loading Lua every frame. Right, so doing a file load and parse of the Lua file every frame, because instead of just doing it once, which they thought they were doing, when they profiled it, it showed that they were doing the 64,000 calls to the Lua file. And it was, don't need to do that. I should load it in once, put it in a string, and then just process the string rather than do the full load Lua of the external executable, right? So sometimes by instrumenting your code, even though your code then runs slowly while you're testing it, you get a better view of what your code is doing. The other thing you get from instrumenting your code and from profiling in general is that you get overall this concept of overall throughput matters, right? I'm interested mainly in how long it takes my user to experience what's going on. I don't care if I use all of the CPUs or how much work each CPU does. If I spin up all 8 cores and it's running at full speed, that's okay, so long as the experience is short, right? Because I'm not actively trying to save energy, usually with a game, right? I'm not trying to make my core run at 20% or run nice and cool. I'm saying, no, I want this experience to run as quickly as possible, right? So even if I could run at, say, 1 core at 40%, I might run 4 cores at 30%, right? Which is a lot more work that the computer is doing. But if I can get that job done faster on 4 cores at 30% than 1 core at 40%, then I can potentially get the user experience better. Because although I'm doing more work, in sense I'm using more computing time, more processing time, because I've been able to spread it across more cores, I can get it done faster. Right? So the faster you get it done, the better overall for your user experience. So when you do profiling, you're not just trying to kind of, oh, can I optimize everything? It's a, does this optimization matter? Does the total length of time matter? How much am I actually saving? So you get what's called core frequency graphs and line frequency. Means this, when you're trying to assert concurrency. So when you're doing multi-threaded code and you're looking at concurrent code, then yes, you have even more complex things to look at than just core frequency, which is the instrumentation, and line frequency, which is the polling, right? So you'll get core frequency, which when you instrument it, every time you call it, it's logged. And line frequency is how often is this line found when you sample the CPU. So one of the things to think about, and probably the biggest optimizations that you guys can do, are not on single line of code optimizations, right? Because I can go low level and get kind of freaky optimizations in some bits of code, right? And you can go down in C and C++, you can go down to assembly code and write your own damn assembly if you really think that you can beat the C++ libraries. You're probably wrong. You probably can't beat the C++ libraries because, you know, Strauss-Drop and the compiler optimization people have spent many years trying to make their code run fast. So you're unlikely to beat them. But if you go down and try and do crazy bitwise optimizations on your code and try and get things running faster, usually that does not have as much effect as big structural changes. Okay? And one of the most important parts of big structural changes is actually on memory accessing. Right? Memory is what tends to slow us down now rather than CPU. Right? So processing, it used to be like number of cycles would be what you'd optimize. Now, what we optimize is actually our memory accessing. So if we have a look at your CPU, what is the CPU actually doing? Right, so we have 4 cores. You're comfortable with 4 cores? You guys have done the operating system course? You understand cache level 1, cache level 2, cache level 3, and RAM? Right, okay, so when we look at optimization, this is for a bit older machine now, but still the numbers are about similar. So core to L1 cache, 4 cycles, right? So you've got, if you're in memory on the CPU and you want to like use the memory in the L1 cache, then you're still taking 4 CPU cycles to get there and back. Right? So your CPU does 4 things while it waits to get a piece of memory. Right? If you're at level 2 cache, it takes 10 cycles. So it's spinning for 10 things. Like, I'm waiting, done. Right? and it gets the stuff. So it sits there many cycles. As soon as you have a cache fail on level 2, you're out to level 3 cache, and then you're up into 40 seconds. Right? So it's 40 cycles, right? So 40 updates. Now, I was having a look at some code, and I can share the code, which was an assignment from, as part of an exam from Trondheim, and it had the difference between a vector for the snake game. Have I talked to you about the snake game optimization? Nope. Okay, so this was an algorithms exam, right? So you guys have done algorithms exams. This was an algorithms exam, and it gave you code for a snake game. Right? And the code had the snake represented as a C++ vector. Right? It started off as vec4. And then it said, okay, write code to move the snake. Right? So, and the idea of the code was to write something that would go, you take the first one, move it to the new location, and you'd step through the vector and say, like x+1, and you'd move each segment into the place of the one before it in the vector. Right? So you just step through the vector, updating x, y position. It then had a question related to linked lists and said, well, you could take a snake, and instead of treating it like a vector and moving it, and and traversing each x, y position and updating them, would be to use it as a list and then do a take from the tail, right? So do a delete from the tail and insert at the head. And then you only have to touch the two nodes, the head of the snake and the tail of the snake, and then you can just move the snake around the screen just by taking one away from the tail and putting it to the new head position. No? So that would be the linked list implementation. You guys can understand how to do that? And when you eat a new apple, when you eat something, you just don't delete. So the tail, it stays where it is, you add one to the head, and then you keep doing the delete and add, right? And so the snake kind of moves just by touching the head and the tail. And what the lecturer wanted to say is that that's more efficient than doing the vector update. Right? Because if you do order notation, with the linked list one, you're doing one insert, right? One addition here and one delete, rather than having to touch every node along the snake. So how long do you think the snake needs to be before touching those 4 bits of memory, right? Going through and actually updating those 4 bits of memory is slower than doing a C++ add to a linked list and delete from the linked list. Right? Because, the touching vectors are pretty fast, right? And once it's in, because with the vector, it's in L1 cache, right? Because you've got, it's just, the struct is just a few integers, right? So you've got it in L1 cache. You're only touching one of those, rather than creating an object. How long do you think the snake would need to be? And which ones do you think the linked list is faster than the vector? No. And how long before a single append and delete is faster than having to touch every point in the vector? Any guesses?
I would guess when you have to move up to the next level cache or something like that.
So how long would the snake need to be, do you think? How many things would you need to touch? Because there's only 4 cycles out here. So and each addition is going to be a cycle. So you're going to have to do some. Any guesses? Just give me a number.
25.
Excellent, that's a good number. It's out by almost a factor of 10, so it's 200, right? So once your snake was 200 long, actually going through and changing 200 XY positions in a vector, then started getting slower than doing one append to a linked list and one remove. Right? So if your snake's less than 200, you should just physically go through the entire vector, updating every XY position, than trying to create add a single object to the standard library's linked list. Right? That's because when you append to a linked list, it has to allocate memory, it has to do pointers, and they have to kind of reorganize themselves. And that memory access and memory allocation is incredibly slow. Then he asked about, then the snake, the second part of the code in the snake was colliding with itself, right? So, you know, in standard snake game, when you collide with yourself, you're supposed to die, right? Collide with yourself or the walls. What do you have to do to check if you've collided with yourself?
See if the head position is the same as the tail position. Well, that's only when you collide with your tail.
Where else could you collide?
Well, the entire tail. Like,
on your entire body.
yeah.
So with a linked list, what does that mean you have to do? You have to traverse a linked list, checking every node in the linked list to see if it's one that you're about to hit. Guess how much slower that is than loading a vector and going through a contiguous block of memory that you can load as one operation into here and then run through the block. A shitload faster is the correct option. And so there is, for a snake game, there is no point at which a linked list is a better optimization than a vector. Vectors kick ass in C++ in every way, right? If you want to do something fast, you do it in a vector, right? There's just the implementation, the memory handling, everything works very well with vectors, right? And, you know, you can even do some clever stuff in your vector and make it look like a linked list. So instead of going through and changing every XY position, I did that because I said I want to move the snake. So I moved every XY so I could look and see. But you can actually treat the vector as a circular cube. Right? So what you do is you actually just change the XY position of the tail, right? And then change the index of the tail in the vector. So you do exactly the same as you would with a linked list, except you just move the tail index along. And then I only have to touch the vector once and update it once because I'm just updating a part of my vector memory rather than actually doing a linked list, an STL linked list, and putting things in, right? So I can make my vector run like it's a linked list, but stored as a vector rather than use STL linked list. And that's the problem with order notation, because you guys have done order notation, yeah? Big O notation, N squared, linear. Our international students, you've done in order notation? No? So maybe you guys have already realized that order notation doesn't make much sense. But the idea of order notation is you can kind of work out how something scales. But unless you actually understand the memory order of a function, just the processing order, the number, like, oh, it's done an add to a linked list, it's done a delete from a linked list, that's 2 operations. That's faster than n operations. The answer is, well, maybe not, right? Because depending on how your memory is structured and how your memory works, it could be that n operations might be faster than 2 operations if those 2 operations are very, very slow and your n can be cached or can operate differently. So understanding that it's your memory that is the slowest thing now on CPUs. Physical distance, right? The reason why these times are different, you know why these are different lengths of time? Why are they different lengths of time?
Just as you said, physical distance from the...
And what determines that? Why does this? How do we have a factor for how much distance costs? Do you know what those numbers come from?
Electricity.
Yes.
Physics.
What's the speed of electricity? No, not quite. It's about it's about one. So the AC. So current travels about 1/3 the speed of light. Right, which is when you create an optical board, you pump light in, you actually get faster transmission. So light-based rather than electrical-based things will move much faster, right? Yep.
Is that related to the type of method we're using?
Yes, there are also metals that conduct more slowly and more quickly and things. But yeah, so we are trying to deal with it. But physical distance costs you time, right? So the further you have to travel to get to memory, the slower it is, right? So actually, one of the problems with sending stuff out to the graphics card is the amount of time it takes to send the data all the way across the board over into the graphics card. Right? That's actually a physical cost of time, right? And so understanding and optimization isn't just, can I make this piece of line of code work? It's often, okay, where's my memory? Have I got my memory loaded? Can I do everything I need to with my cached memory that I'm going to do with it before it has a cache fault and gets unloaded? Right? Because if it gets unloaded, it's going to take you a long time to get it back and to process it.
There's another factor. What about size of memory, right? Because random access in the larger memory bank, otherwise we would just say, well, let's keep the distance short and have a massive memory immediately, a massive cache immediately attached to the CPU, right? But the random access is the reason why we have this, staged sizes, right? So level 1, 2, and 3 cache.
Well, yeah, because it's the thing. If you want to have something large, you've got to have space for it. So it's going to be further away, right? Just because it has to be bigger, right? So locality. Also, you have these caches which are smaller, physically closer, right? So yes, if you could have one big one, but if you have one big one, then it's each part of this big one is further away, right? So the kind of imagine the bigger it is, the further away it has to be, right? So yeah, there is that kind of challenge of if you you could have like a massive supermarket, right? But if you have a massive supermarket, then the bread and the milk are in the far corners of your massive supermarket. Whereas you could just have a dairy that was next to you that just had the things you need to buy all the time are right next to you, and the things you access infrequently in the massive supermarket, you just go in, you kind of go into that massive supermarket, right? But you can imagine in the massive supermarket, you can like 1 million cartons of milk. But if it takes you 20 minutes to walk to the cartons of milk, then that's the massive supermarket with all the cartons of milk over here. Whereas really you just want one carton of milk, one loaf of bread, noodles, Grandiosa pizza, a bottle of Coke. I don't know what's in your local dairy cache is the things you access most often, right? And if you want something unusual, you have to go out to main memory, right? And each of the CPUs, each of the cores, will have its own local store of the thing it's accessing most often, right? And one of the problems is you can only process it here in your pantry, right? So you can imagine like this would be the pantry, this might be your local store, and this would be the supermarket. But you've only got a certain amount of capacity, and so you have to store it here, which means you have to throw out the thing you've got to load in the new thing you've got. So the new object you brought in, right? And if you brought in a big object, it uses up all the cache. You invalidate everything, and you get some really bad behavior, bad performance when you get thrashing, where you are constantly having cache fail, right? So when your memory is large enough, so every time I try and process it, say I'm processing an image, if each line of my image is large enough that it overwrites this, every time I bring in another line, and it overwrites the whole thing, right? Now, when accessing images, you guys know about two-dimensional arrays? You did access by row and then by column, so row internal loop. That's all to do with how memory is loaded in, right? Because if you're doing column access, so if you go the first row, first column, second row, first column, third row, first column, you take that entire column memory, you put it in cache. You then access one part of it, drop that entire thing, grab the next row of memory, put it in cache. So then every time you're accessing, and if your image is big, you might be bigger than L3 cache, right? There's a possibility.
It's not only for images, it's for anything that is going on.
Anything that you're jumping through memory and accessing it at kind of random positions or later on, if you can try and find a way of processing it sequentially, it'll go much, much faster.
It's the same like if you have some game objects in a struct and you keep vector of it, and then you need to process it. linearly. If it's big enough that it exceeds the L1 cache, you will lose that performance. So it's better to have an additional data structure which only has that bit that you really need to process in a vector, and then do that sequentially, right?
Yeah.
So it's not only for images and not only for 2D arrays, it's also for single D arrays with structs and how much you keep in that struct.
So if you've got your game objects, if you keep your full objects, right, a full object here might use up this whole cache when you bring in the whole object, because you just want the X value of it, but you have to bring in that block of memory. So it copies that block of memory into here, you grab the X value out of it, you then get the next object in your array, and so it throws that one out, copies the next whole object in. Right? And suddenly you're stepping through your X in each object, and it's really slow because your memory is getting invalidated and you're having to do the full copy in and out of memory. So if you know that you're going to do a lot of accessing of the X value, one way is you create a new struct that just has the X's in it. Right? And then when you want to know all the positions of the X's of the values, you just load that struct in, and suddenly this has just got all the X values in it. And you can skip through all of the X values for every object, and you don't have any more memory accesses. And so you just run through and quickly access all of those things. It does make your code look a bit shit, right? Because instead of having an array of structures, right? So normally what we do is you create an object, and then you create an array of those objects, right? And that conceptually makes sense. Now what you do is you, instead of having an array of objects, you have an object with a bunch of arrays in it, right? And so instead of having object 1, which has its X, its Y, its Z, its health, its agent number, its mesh, right? So you have that object, and then you have an array of those. You have 5 arrays in your object. You have an array of X's, you have an array of Y's, you have an array of Z's. And you just know that object 1 is all of the 0 elements out of those. And object 15 is, okay, well, if object 0 is 0, object 1 is 1, object 15, you just go through those arrays and say, oh, grab me the X of position 15. Grab me the Y of position 15, grab me Z at position 15, grab me name at position 15, because you've got synchronized arrays of memory. Very ugly, right? Not good conceptually for understanding what's going on. Great for performance, right? And that's one of those trade-offs that you do. And that's why I say profile the shit out of this, right? Because if you don't know that you need to do that, you've made your code worse without getting a benefit, right? So you have to know that that accessing and going through the X values are what's making your code slow. Once you identify, that operation is making my code slow, that for loop where I have to go through and collect all the X values, that's making my code slow, right? What I'll do is I may have to restructure my code so it performs better in memory, right? But you only make those decisions once you know that you've got a critical performance issue.
And you always do it data-driven. So you don't optimize things because you think it's better. You have to have evidence that your changes actually improve the performance. So you have to measure it. Measure it before the changes and measure it after. And if it improves the performance, you're doing a good job. If it doesn't, you will revert back. So you don't change things to optimize things because you think, okay, that's going to be faster. Never do that.
No, and unless you've got
most of the time wrong.
Yeah, most of the time you do get it wrong. One of my favorite ones for getting this wrong was for loop optimization, right? And I think I showed you guys counting down in for loops is supposedly faster, but it's not faster under any modern compiler, right? So just turn your optimizations on your compiler and test this, right? You've got to test it in the raw, test it in your optimized version. If your optimized version isn't faster and is conceptually more complex, go back to the conceptually better, simpler code. Yeah, stick with the simple solution. Cache is a big lookup table, the address book ordered on least significant bits, NY associated, stored several items in each location. So One of the things that we look about in terms of memory optimization is reordering and hardware prefetches. Some of this you don't have control over, right? So when you're doing optimizations, you might check an optimization for on a particular machine and go, right, on my machine, this runs like at 0.2 of the normal performance, right? So it's at 20% of the original performance. So it's run 5 times faster, right? And then you go, when we change to this other hardware, it now runs slower, right? And that can be because in your hardware, you might be prefetching blocks of memory. And so if you've prefetched and it's doing a hardware prefetch, then suddenly running through that memory, it's already prefetched. It's really, really fast. On another piece of hardware, it might not prefetch that, which means when you hit the end, you have to go and ask for that new piece of memory, and you get the whole cycle of it. Right? So hardware-dependent optimizations means that for PCs, and if you're running on a 64-bit machine, sometimes with the different levels of caches, and you've done some size optimizations and it works really well on your machine and all of the machines in the class, someone gets a new machine and they see no improvement because you've optimized for one particular set of hardware, and someone runs it on an old machine and it now runs much slower than it was before because you're making lots of assumptions about where the memory will be. Right? So you can't just test on one machine to say whether you've optimized for it. And if you are making lots of optimizations that are particular to the hardware you're on, if someone rewrites the compiler and updates the compiler and optimizes standard library, suddenly what you thought was a clever optimization is now much worse. The example I had commercially of this was when we were working in Flash, and we were doing trigonometry lookup, right? Because the trig in Flash 8 was really, really slow, right? So you do an arctan and it would just take forever to calculate it. So what we did is when our program started up, we loaded up a table, a 360 item array, and we do each angle and we did the arctangent on it and still cached those values. So now we had a 360 lookup table of each degree, and then we just floor, each time we needed to find an arctangent, we'd just floor the angle and look it up in the table, right? And we're running 10 times faster than actually using their arctangent code. We tried it on Flash 9, and suddenly we were running at twice as long as the arctangent because they completely re-implemented the way they did math, and they made their math run faster than our lookup table. So we had to ditch all of our lookup table stuff because now that was the slow solution because it was having to load in memory of those 360 item array, whereas the arctangent had changed to have a pre-cached value system. So when you accessed it, it pre-cached that number. So if you asked it the arctangent of 300 degrees, it would go, oh, you asked me that a frame ago. I stored that in local memory, so now I can just do a lookup on that. So they changed the way that the compiler optimized Flash code, and then suddenly it had function lookup and function caching, and now it was running much faster than we could do because we weren't in control of their arctangent code, so we couldn't do a cached value system, right? And our own cached value system was not as good as theirs. So hardware prefetches, if you want to optimize, one of the first steps to do is to tell the compiler everything you know, right? If you know something's going to be const, tell the compiler it's const. If you know it's unsigned, tell the compiler it's unsigned. Don't just make it int and go, oh, it'll always be positive. If you know it's always positive, you say, right, this is unsigned. I know it's always going to be positive. I know it's never going to go 0. And that will help the compiler optimize your code. Right? So the more information you give about stuff, the more the compiler can do. In modern C++, if using autos allows the compiler to do optimizations, right? Because it might work out a better data type for optimizing your code than you would have thought of, right? So instead of using a U8, if you go auto and the compiler goes, oh, I know if I keep these all as U16s, I'll be able to fit them in the cache better. I'll just optimize using that. And I'll just switch that auto into what I know is going to be faster. Right? So let the compiler do its job. optimizing your code. So there are some interesting challenges of false sharing with multi-user multi-threaded system, where if two threads are accessing the same piece of memory, they keep grabbing it and invalidating it for the other one. So you have to kind of keep jumping back and forth between two threads, right? So there's a false sharing issue with caches, which we won't go into this time because we're not doing a multi-threaded course. Memory aliasing with the restrict keyword. So there are issues of having shared memory. And when you've got shared memory, knowing when that memory is being copied around and who's copying that and who's got access to it. So you can actually do some restricting on memory accesses. So you can say, no, this is mine, don't use my memory, right? And so each core gets its own cache, gets its own memory copy. Organize data and loop in the direction of your memory, right? So as we're saying, yeah, organize that data, loop in the direction. Block code using squares of a larger array. So if you're doing image processing, right? One way to do it is say, okay, if I know that I'm going to have to go through the entire image, right? Instead of having my memory completely stored as one massive long line, right, and filling up a massive array, I could pre-organize my memory. So I say, well, actually, let's take this big image and turn it into 9 sub-images, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then if I know I'm accessing this block, I can just load in this sub-image and process it because I've collected all that memory into one location, right? So there are ways that you can reorder memory. In fact, one of the ways of getting, if you're doing imaging processing, right, there is a way of doing the Gaussian blur. You do it as like a 3-dimensional Gaussian blur is two 2-dimensional Gaussian blurs, just a piece of math, right? And so 2-dimensional is faster because you only have to go this way and then you go vertically. Going vertically is going to be really slow. And so what you do is you do an image transpose before, and there's a fast memory access to do that, where it just basically reorganizes your memory in one hit to do that. And then you step through processing the image in the transposed version of it, right? And so when you do that, and when you create a fast transpose and then do a memory aligned lookup, you tend to get much better performance. Right? Pack code, don't even interleave your code with sparse access. So when you're wanting to process things quickly, rather than creating a big array and then saying, oh, I'll have you at position 1, you at position 10, you at position 30. Once you start having sparse arrays, when you try and bring them into cache, they have a whole bunch of bank values. So what you do is you pack your data. Try and get your data to be packed tightly together. It might cost you a bit of processing time because you have to work out, oh, you're actually position 10. Right? So you can't just do grab me the thing at position 10. You say, grab me the next item and see which position it is. Right? So it can take you a bit longer, but if you're really sparse, that's still going to be faster. Right? Because sparse code is really slow. So there are so single instruction, multiple data. There are ways. So SIMDs. There are ways of doing various optimizations, inlining of things to avoid it creating additional memory on your stack. Right. So you guys know you have a heap and a stack. Do you know the difference between a heap and a stack?
You should know.
What's the difference between the heap and the stack? What's stack memory and when is it used? Can any of you remember this?
I know stack memory is the one where you like add on the stack afterwards.
Yes. And when does that happen?
I don't remember which of them was the one you normally use, and which is the one that you have to specify. Because I think one was used when you use like pointer memory or
something like that, and the other is like for regular ints and like compiler normal primitives or something.
Yeah.
So
So you've made some of the connections, but you haven't quite got it. Like, you're right, but there's a reason why you're right, and you haven't given the reason why you're right, right? So when you do a function call, that is stack memory, right? Because so main is a function call. So when you talk about, normal, you mean ints described in the top of the function, right? Or described in the body of the function. Those are normal because they're inside a function, and therefore they're stack memory because they're put on the stack. When you do a new somewhere in here and say, hey, I want a new thing, that's when I get heap memory, right? Because I say, oh, I'm going to allocate some memory, go grab me some memory. It doesn't add that to the stack, it grabs that from the heap. Okay, so and every time you call a new function, you add new memory to the stack because that's a new scope memory that is now being added to the stack. And so your stack gets bigger and bigger and bigger as you go down in more and more functions. Okay? So when you inline memory, instead of having a separate stack for this function, you put it into the original stack. Right? And so you reuse values, and you have to watch out for some of that, but you can decrease the amount of stack you're creating because you're having less or fewer function calls. But the stack is related to those kind of, if you create in a kind of int I, that's going to be on the stack because it's in the function. If you ask for a new malloc, then it say, oh, you want some new memory? I've got a heap of that, and it goes to the heap. Right? So when you're kind of understanding how your memory works and you're trying to minimize memory movement, then yes, thinking about stacks and caches. Most of your compilers now do a lot of inlining for you. So they'll take your functions and they'll inline them. They won't actually make a function call. They'll just put the code directly in the main body, right? And try and call the names of your things to create scope so that it doesn't break scope. Okay? And that will affect how your program runs. Yep, I've got 8 minutes before I have to go. So pipelines and branching. So I have a couple more slides to go. So do you understand your CPU and the CPU pipeline? Do you know what a CPU pipeline is? Have you heard the phrase before? Right. What does a CPU pipeline do?
It's the one that puts like instructions to different like
a queue of instructions.
A queue of instructions.
Yeah.
Excellent.
Yeah.
And how long your pipeline is the length of time it takes for one instruction popped in here before it actually gets to finished. So I can kind of queue them up. Huh? And the length of your pipeline tells you kind of how many stages you've got and also what you're doing to try and to optimize things. So we're around about, Windows, so the I and the core ones are about 20 cycles long, right? So there's 20 stages in your pipeline. And giving a longer pipeline doesn't necessarily make you slower. It might increase latency, right? So the length of time it takes for one operation to get from here to here might increase because there's more stages. But in terms of number of operations processed per second, it might not decrease that amount, right? Because if I get a hose and I turn it on full, right? Then the amount of water going in the end is the amount of water coming out the other end, yeah? And if I have a wee short hose, I get the same amount of water out. For a really long hose, I get the same amount of water out. It just, when I have a long hose, it takes longer for a single bit of water to go from the nozzle all the way through the pipe to get out the end. Now, one of the problems is if you have an if then else in your code, particularly on GPUs because they're really bad for this, but if you have an if then else, it's like taking your hose and unplugging it, then plugging in another hose. Because if the if fails, it goes, oh, I have to validate everything in my pipeline. So in this case, all 20 of those instructions are dropped, and I have to load in another 20 instructions. And so I get all the latency of filling up my pipeline again. So an if-else check for optimization can be really slow because it has to try and work out what to fill this instruction with, right? Because if I'm going to do an if tells me either do this block of code or do this block of code, right? Now, if I have an if and an else, I don't know what block of code to run, right? So one way to try and get it optimal is it kind of does predictive caching, where it says, okay, let's assume that that if is going to be true, right? And it will fill it with that. Or it does an optimization which says, okay, let's assume that if statement is the same as it was last time, right? So if you're doing a for loop and you're saying like, you know, you're running through and saying if less than, then continue, it goes, oh, I'll assume that it's still less than. And so I'll fill it up with all the instructions in the for loop. So when it gets to that if, it doesn't just drop the for loop and have to reload them, assuming it was false. It will assume it's true, load up the for loop, and then just continue. And when it gets to the end of the for loop, it goes, it invalidates that, oh, this is now bigger than 10. Drop all that code of the for loop I put in, and then start adding in the instructions after the for loop. Right? So at the end of the for loop, you lose 20 cycles, right? Because you've just had to unload your pipeline. Right? You understand how that works? Dropping the whole pipeline? Well, that means that if you're doing coding, if you've got lots of ifs and else's in your code, that's probably going to be slow. Yeah, because if it keeps changing back and forth between true and false on those cases, right? If you're doing a mod 2 and like even and odd operations, it's going to be invalidating the pipeline every single operation. And so you're going to run really slowly. So what you do is you try and organize it so you step through all of the true cases and then step through all of the false cases. Right? Just don't leave your if then else and do the two different things per operation. You say, right, can I group these so I do all of the true things first and then all of the false things together? Right? So you don't get this pipeline invalidation. And in fact, often two ifs are better than branching. Right? If and then another if later. So you can block those because it can then assume one's true and run through that much faster. Right? And so it generally can make a better decision. If and vector, so if and vector are even better, so avoiding double logic. So basically, if you can separate your if out and make two vectors of the true parts and the false parts, then you run through memory much faster, right? So reorganizing your logic, moving your logic outside of processing. So if you do your logic first and then go, right, now I've got all the data I need to process in one place, now I run and process it, rather than have your if right down the bottom of getting everything and then doing the last if check to see if you do to see what bit of code you run, right? Separate those out, make them two different for loops, those sort of things. But again, only if you've got a profiling that says that this bit of code is slow. So if you keep logic simple, then you can use a lot of it. But if you use branching, then it's going to be slow. So some stuff that might be true, and this stuff changes every year. So basic tuning, improve your memory access, improve your locality of reference. So if you can just reference locally data, then that's better. Reuse data, where you've got data on the CPU, use that shit as much as you can before you lose it, because it's going to take a long time to get it back. So stride minimization is to fit the cache. If you can work out how big your cache is and you're really struggling for optimization and performance, then you can try and grab a length of data that is the same size as your cache. So process at the same size as your cache, but then different cache sizes will mean you'll perform badly. And if you make your stride large enough so it has to invalidate the cache every time, you do this, and then you invalidate the cache and you get that one little bit extra, and you need a whole new cache load for it. So suddenly you go from being right on performance to being half the speed that you were going at, right? So you've got to worry about your fit to the particular CPU. Avoid indirect addressing. So if you are really trying to optimize, you don't go square bracket I dot square bracket, like grab a subarray, and so array square bracket, because that does a whole bunch of lookups. Pointer arithmetic is faster if you really need to stride through memory, right? I would virtually never do that with STL and C++. Use vector and use the iterator in vector and autos, because the compiler will generally optimize that completely, right? Use the parallel capability. If you are in C++, look up OMP, right? Look up the OMP calls and OMP parallelize. It takes you about 10 minutes to work out how to do it, and you can take a for loop and make it run on all 8 of your cores in about 10 minutes of reading online, right? So OMP, if you want to make your C++ run faster. So there is a whole bunch of stuff here on using parallel optimization. If you're interested, we have a bunch of exercises and a bunch of lectures that you guys can look up if you want to study some optimization over Christmas, perhaps. Okay, so other questions around optimization before I have to flee now to go and see my son, because he's having a PPT meeting at school, so I'm supposed to go. And Rachel will probably ring me in about 30 seconds or so. But I have 30 seconds, so what are your questions? Optimization. Do you see some of that data? It's a big slow thing. But only optimize once you profile. Profile, then, and it's really crazy because this will be much faster. You test it and it's slower because the optimizer is already screwing around with the way it does memory and you just can't tell what it's doing, right? You are so far now from the metal that unless you're programming in C with the optimization off, you really don't know what's going on, right? So once you're in C++ or C#, or you've got a game engine, yeah, trial and error is basically how you get optimizations to work. But understanding that memory is going to be the slow thing rather than CPU cycles. Right? So think about how you organize memory. Okay. Cool. Right. So Christopher will probably pop in and see you next week on Monday.
What's the topic?
No, they're reporting on their progress. But we'd like you to make videos so we can watch them. All right. So try and make a video update. So Beastie Boys are great. Was I right? 30 seconds? That was about 30 seconds? Maybe a minute? On my way. I'm in 254. Okay. Yeah.
So you guys have questions? Because we can stay for another.
Yeah, these guys are safe.
Yeah, I actually don't have visuals to do.
I have it here with the profile on the Pro. Visual Studio 15. Oh, that's only the community. I need the
full one. I only have the community.
Visual.
Yeah, you go.
Ultimate. So 13 has ultimate, so you can show them on ultimate.
Right.
And I'll leave that stuff there.
Yep.
And I'll go. Yep. Okay. So well, you can stay and you can watch the Visual Studio profile, because you can run up the profiler. If you run up ball game from Visual Studio 13.
Yeah.
So so with 13 and open project. I know, cancel with recent projects. Recent. Too many graphics exams. If we open and I look for Git collaboration, code, game.
Should load.
Yep. And it should have, if you go to analyze, you get full profile diagnostics. Oh, so mirrored screen. So we have to mirror the screen. So he's going to mirror screen. I'm going to go and look at that. So if you mirror the screen, you should be able to.
What one is going on now?
Oh, yeah.
I think
All right, let's see. If it actually compiles and works. Right. So just before we do that, this stack versus heap thing is kind of important. So if I have a function and I have a body of my function and I have to do something, right? So some parameters come in and I have to have an array. So let's say I have an array A of some size, okay, of ints. And then I can do the same by saying I have a pointer to int, and then so those are two alternatives, right? And then I have a loop which kind of does something with my data. What's the difference between me doing this, or me doing that A is just a vector of ints? What are the advantages and disadvantages of doing the three different options? And which one is on the heap and which one is on the stack?
To the top, they create runtime stacks.
Yeah, so these ones are on the stack. This one is on the heap. So heap, stack. What are the hard limitations? Can I have, like, 1 GB image on the stack? No. So, there are some hard limitations that here I have a huge size, right? On the heap, I am kind of unlimited of how much stuff I can store. Here are some limits, right? So if you really need to store something really big, you're kind of in this category no matter what, right? But if something is reasonably small, you can choose. You can go here or here, right? So what is the advantage of doing, let's say we are in this kind of a middle category, not too big, we can use either, all three of them. So what would be the objectives that you would kind of consider choosing? One obvious one that you see here is that I actually need to know what the size is, right? So if I know what my upper limit is, then I would probably go with this. That one is the fastest. Why? It's already there. The moment I call the function, it's already pre-allocated. It's already on the stack. I already have this space on the stack for that buffer or whatever it is, right? There is no allocation needed. It's already there. It is very fast access because it's local to my function. So I will be using relative indices on the assembly language to kind of access it. And it's, that's the fastest, right? So that's why often when we do networking and you have to read something, you know what the maximum payload is, and then you pre-allocate the buffer using the stack. You read stuff into it, you process it, and the moment you quit your function, so the moment you go out of the function, it's cleaned up, right? And this allocating and deallocating, that has to happen no matter what. Like all the local variables for the function, they have to be on the stack. So it costs you nothing, right? Because this is automatically happening. This you causing to happen. It's additional work that you have to do, right? So if you know the size, this one is the best. If you don't know the size, now you have those two options. So which one is better? Use a vector or use a malloc and mu and allocate memory yourself and have a memory for yourself. Which one you think is better? Yeah, why?
It's what Simon said earlier, like you don't have the access another block of memory.
Yes. So they put a lot of effort in making sure that kick ass in terms of implementation, and also it has all the performance benefits of having a continuous memory block anyway, and you will be much safer to do this, right? So if often you have choices of stack versus heap, and your choices of stack are always better than the heap. So you kind of only falling back to heap that when you have to, right? And when will you have to fall into the heap? There are many cases, but one we already discussed. If you have kind of a huge stuff to process, well, then you have to use heap. When else? Yeah? Yeah?
Yeah, the X is like on the object.
Yes, so I mean, the stack is very limited. I mean, the lifelessness of the stack finishes when you quit your function, right? So for anything that lives beyond your function call, you have to use heap. There is no other way, right? But within a single function, anything you have to use or create or use for your processing, that, you know, your definitely preferred way is to use the stack.
Could it be partially rational that function programming is more efficient from this perspective?
Exactly.
Because of side effects, right?
Exactly. So that's why there is this new kind of a wave of paradigm shift a little bit from like object-oriented programming, where we did use heap a lot and we have side effects of our functions operating on the classes and so on, to kind of more functional programming where you have stuff that you need to process coming in, and the moment you quit your function, you're done. You don't really have like persistent side effects that kind of depend on something outside of your function, right? So in many circumstances, and in C++ as well, using lambdas and using kind of a functional programming design patterns, you can reorganize your code to be actually more efficient and more effective use of a stack. So that's the heap versus stack debate. There was one more thing that Simon was talking about, which I also wanted to comment, is the loop prediction. So avoiding else statements. That's, yeah, we were discussing it in the style, right? It's always better to reorganize your code just to have an if and then the rest without the if else. But it's, in terms of performance, it's also beneficial. Having said that, you should usually try to organize your loops in such a way that the condition is the most frequent one, right? So he mentioned like, okay, how often you know, the condition triggers, right? If your condition triggers 50-50, true or false, it doesn't matter. But if your condition triggers most of the time true, then it's, you know, usually better for the optimizations on the CPU level and on the code level, so that your if statements, if you're writing an if statement and you're putting some logic in here, you have to ask yourself, okay, how often will that be true, right? If that is true, like if I have a choice, I have a condition and I have two cases and it's 50-50, then it doesn't matter. But if it's like 50-95, right? Put the 95 case as the condition, not the 5 case, right? Okay, there is a caveat to that. It only matters if inside your kind of inner loops, right? If you have a function and you're checking for an error, you're saying, okay, if error, and that almost never happens. It's like 0.0001% of time. That's okay. I mean, you're checking it once, right? It's not in the loop. It actually doesn't matter that much. But it matters if you have an inner loop and you're doing something inside the inner loop and you have two cases, then make the if statement to cover the bigger one. Most architectures and most CPUs, and it's not even the compiler. It's often the CPU architecture is the, you know, Intel CPU, which actually does the branch prediction for itself. So the compiler just generates the code, the 2 blocks of code with the split, with the jump, and then the CPU will kind of take some statistics. And often what the CPU is doing is kind of keeping track of how many positive and how many negative branches you hit. So then it does the branch prediction of what to load into the pipeline, right? So it actually is doing that. But the first time it hits the if statement, it doesn't have any data. So it will assume, most of them, they will assume the if statement is for the bigger case to be true, right? So then you will have a little bit of a performance benefit. So that was that thing. And the final thing I wanted to comment on was about the cache as well. So you have a data cache, which Simon was talking about, and that's why you're trying to optimize the hit ratio. So there is a metric which is called cache miss, right? Yeah, it's not right. Cache miss. So you in your profilers, you can actually observe how many times while running a function you had a cache miss on a line 1 or line 2 or cache level 3, right? And then you're trying to optimize that you're missing the cache least frequently, especially in the inner loops. But that's about the data access. The cool thing is that with multi-core CPUs, there is something which is called code cache as well, right? So, your program needs to be loaded before it is passed through the pipeline for the CPU to execute it, right? So you have the data cache, but you have also the program cache, which loads your functions. And what we've been doing to really optimize on a multi-core machines, like if you have, you have 4 cores, right? You're writing a function. So you have a function which you need to process. So you have some sort of work to be done, okay? And it's just a sequential piece of work. There is no parallelism there. Of course, if you have some parallel, like you can do graphics and sound and some AIs separately, then of course you use multi-thread and multi-threading paradigm, and you have multiple threads occupying the cores, right? But imagine the case that you only have one task to be done, and you want to do it as fast as possible, and it's a sequential task. And then what would you do? Like, how would you speed it up, benefiting from 4 cores? Normally, you just write a function, and it's executed on one of the cores, right? And that's it. So there is no benefit, right? You occupying one core, you're doing it, and then you get the result. But what if you want to use all 4 cores? How would you do that? Well, you can make yourself a pipeline, right? What you can do is you can say, okay, actually, I know I'm doing this, okay, that will be called number 1. The results at this point, I can share to the next pipeline, to the next partner in my pipeline. And then the results here, I will share to the third one. Okay, let's see, we just do for 3. So now I have a piece of code here, piece of code here, and piece of code here. And then this function in the inner loop is called. It does that. And then the results are kind of in a shared cache. And then when I'm done here, I can start doing the next packet. Let's say we're doing something for network. So the moment I finish those 6 instructions, I'm done, and I can pick the next packet and start doing what I was doing before, right? So I'm kind of much faster now to accept the packets. And then this guy takes the partial results and does its job. Again, it's doing, faster than, because here I have to spend, let's say, 1 second to do the whole thing. Here I'm spending 1/3 of a second, depending how I arranged it. So now I'm kind of processing my incoming packets theoretically 3 times faster, right? Do you understand this? So now the clever thing is that you can ask, okay, when I'm doing this loop, is my code on this core invalidated, so I have to reload it? Because if I do, I'm losing performance, right? It's a little bit counterintuitive, but if this function is too big, if I have a little bit too much logic here, what happens is the CPU loads piece of code. Let's say I exceeded it at that line. It loaded that bit into the code cache, decoded the pipeline, started doing my loop. And at this point, it says, okay, I need to execute next instruction. And it says, okay, it's not in the code cache. We need to trash it and load the next bit, right? So I'm doing a cache miss on the code, not on the data, on the code itself, right? So sometimes adding like 1 extra instruction to your function makes the code run so much slower than if you just take this instruction out and put it into your next block, right? And this is so much fun to do, like if you have a profiler running and you're kind of calculating the code cache misses, because sometimes you just say, okay, I have a function. So you have a function and you say, I have, so you have a function, you have your code, and then you said, okay, I need one extra Boolean variable, so, or, one extra int. So you say, okay, I have the, I'm writing Go too much. So I have an extra int variable, that's 4 bytes, right? And then suddenly your code runs much slower. You're not doing anything different. It's exactly the same code. You just, allocated an extra int on the stack, and suddenly your code runs much more slower. And the factor is usually like 10 folds or something, right? So it's like, okay, I can delete that line of code, and suddenly my code runs much faster, right? So this kind of code cache misses are kind of important if you really like optimizing for throughput and for performance on both the data cache and the code cache levels. So, and this, like, no tools will do that for you. You have to like play with it manually, right? So as Simon was saying, that optimization is a bit of a game for programmers. It is kind of a game because you have some sort of a feedback loop, and you just manually like playing the system to achieve like what you really like. You don't know what's the upper limit, so you're kind of exploring it, right? Yeah. So those were the three kind of things that I wanted to add. Right. So do you have any questions? We can try to see if I can get his code. Oh yeah.
So when it comes to code caching, you want more operation on one line instead of taking the operations like on different lines. So you say int a semicolon a equals 100 is lower than int a equals 100.
No, it's not. So it's exactly the same. So a function is like a block that the runtime system needs to load and allocate the stack. It's like they call it like a frame, right? So every time you make a function call, a frame is allocated on the stack to contain the code and the data, and then the CPU will kind of decode it, right? So that your function as a blob has certain size, and every time you allocate an extra variable, that size grows a little bit. Every time you add an extra instruction, the size grows a little bit, right? So as long as this size is small enough that it fits into a single cache entry on the code level, then it will be reused over and over again when you have your loop, right? So your loop will not load the code again. It will kind of reuse what's in the cache. So it doesn't need to go to memory to read your code. It's already having everything in the cache, right? And it kind of warms up the pipeline, and then it's super fast because it doesn't need to decode or reuse anything. It just have everything already there. But if you write a function which is a little bit bigger, then while you're executing the function, there will be a cache miss on your data or on your code, right? And then the CPU says, oh yeah, we actually don't have that in the cache. We have to go to RAM, reread the bit that is missing, right?
Yeah, that was my question. So
yeah.
If you are like just on the limit,
yeah,
and you like say int a semicolon and a equals 100, and you go above that code threshold.
Yes. Okay. So in principle, you're right. Your idea is correct. It's just that with the modern compilers, this. So if I say int a equals 1, or if I say int a equals 1, those are exactly the same. Like all modern compilers will do those two things the same way.
Yeah.
So there will be kind of an allocation of int with 1 in it done, optimized already out. But in principle, yes, you're right. If there is something like this that the compiler will not like optimize out, then it will make difference. Yes, exactly. Yeah.
Just to comment on the optimization, the pipelining, right?
Yeah.
It really only is relevant if you have sufficiently large workload, right? Because the level 3
yes.
cache, which is the one shared between cores, is really expensive to use.
Yes,
so for smaller
right.
nodes, you won't have that benefit, right? Because you wouldn't have a shared cache across multiple cores.
Yeah. So also most of these optimizations only matters if you're optimizing on level 1. Like on level 3, things that get so messy with operating system anyway that you don't don't have control anymore. So optimizing for level 3 access makes no sense. So all these optimizations only make sense if you have a very heavy workload, if you're really optimizing your guts out, and if you're really working on level 1. Anything else kind of helps, but it's statistical. Like you have no control anymore. Yeah. And most of the time, you should not be doing that, right? For most use cases, that doesn't make any sense. And it's extremely costly because you have to do it like manually.
So it's also it's the total overfitting, right, to your architecture.
Yes, right? So exactly. Yeah.
So if you have like each frame, you have a few functions that are called like every frame.
Yeah.
Would it be best to assign one function to this ASIC core, so it wouldn't have to reload the functions, or?
Yeah. So usually assigning a particular function to a core makes it better. Also, if you have to do multiple things in the same frame, like you're talking about the display loop, it's better if you just have it as a single function, not multiple functions, right? So kind of try to optimize it that it's like as little stack allocations as possible within your kind of loop. So usually we try to make it like there is a single function which we load every frame, and we try to inline what needs to be done, right? The moment you have to call something, you need to allocate the stack again and so on. So, for those heavy workloads like in display callbacks, try to kind of inline the things, or just have a giant function which does everything, every 90 hertz or something. Yeah. Yep. Okay.
Can you specify this cache affinity on function level? I already know it on process level. So, but can you bring, like, you can say a process, please always run it on that particular CPU. Therefore,
no, you can only do it on a process level. Right. So basically, what you have to do is you have to have a thread which runs your function, and that, you can control that. Right. You cannot control it on on the function level per se. Yeah, it's on per process level. It also makes sense if you can kind of control. So you can control like what runs where. And for our optimizations on those 3 cores, of course, it only makes sense if this first bit works on that particular core, that bit on that particular core, and so on. Because we know then how the data is shared, and like we're reusing it. If they have to be, if there is an interrupt, then it has to be like context switched. You're losing. You're completely losing performance, right? You know what context switching is from operating system? Yeah. So every time you have this kind of optimization and it's subjected to context switching, it goes to hell, right? Because then you're losing all the intricacies that you've put in. So I don't think I know Simon's password.
It's okay.
And I don't think he used this one.
Don't share it on the screen.
Yeah. Right. Sorry. But what we can do is like you can play, like it's not that hard with Visual Studio actually. The tools are kind of integrated. So if you play a little bit and you have questions about particular metrics or how to measure particular things, then we can we can discuss it later. Right. So thanks.
I already missed the thing of writing stuff.
Yeah.
All that kind of generally